All right, so continuing our look into more algebraic attempts at differentiation. This is perhaps the most important lesson, in that the chain rule is something that going forwards, it'll be exceedingly rare that you'll have to differentiate something without ever using the chain rule. Because the majority of functions we can imagine as being a composition of one function inside another. And the chain rule, it allows us to differentiate something like that. And like so many other things, the best way of learning this is just to try it. I'm going to go through these fairly quickly, but make sure you've tried all these first. And so if I look at this function here, I can imagine e to the power of x being inside the sine function. And so the sine function is my outside function. I want to differentiate that first. So the derivative, dy dx. The derivative of sine is cosine. And I leave my inside function alone, and then I multiply by the derivative of the inside function. And the lovely thing about e to the power of x, its derivative is just e to the power of x. And I'm done. We want to make sure we make it clear that this e to the power of x is inside a cosine function, this e to the power of x is not, however we write it. Hence I have those brackets there. All right, this is the same two functions, but composed the other way around. And this time sine of x is inside the exponential function with a base of e. So dy dx, first I differentiate the outside function, which again, e to the power of anything stays the same. So that's the outside function. Now I multiply by the derivative of the inside function, and the derivative of sine is cos of x. And again, just make sure it's clear what's inside the function and what's not. So notice again, same two functions but composed the other way around, which not surprisingly leads to different derivatives. Let's look here. To differentiate this, first thing I'd like to do is rewrite it before I differentiate it with a power instead of a radical. So I have 1 plus x cubed to the power of 1/2. And now I want to differentiate that using the power rule. So the outside function, I have this, I can use the power rule. So I have 1/2 times 1 plus x cubed. Subtract 1 from 1/2, you get negative 1/2. That's the derivative of the outside function. Now I want to differentiate the inside function, which is nice and simple. It's a polynomial. I have the derivative of 1 is 0, plus the derivative of x cubed is 3x squared. So at this point, just to clean this up a little bit, all I really need to have in my numerator is 3x squared. In my denominator, I have 2 times either 1 plus x cubed to the power of 1/2, or I can write it in radical form like we started with. 3x squared over 2 times the square root of 1 plus x cubed. All right, and then lastly for this question, similar functions, just a different order of things. So in this case, the outside function is the cubic part to the power of 3. So again, use the power rule. So I have 3 times 1 plus the square root of x left alone to the power of 2 times, now I want to differentiate the inside function, which actually I'm going to just take the time right here to rewrite as 1 plus x to the 1/2. Because when I differentiate that, the derivative of 1 is 0, plus the derivative of x to the 1/2 is 1/2 x to the negative 1/2. All right, and again, just to clean this up a bit, this is the same as 3 times 1 plus, I'll go back to my square root of x squared, and this is right here, I have just 1 over 2 times the square root of x, if I clean up that, which means if I write this as a single rational expression, or a single fraction, what do I get? I get 3 times 1 plus the square root of x squared all over 2 times the square root of x. All right. So again, just lots of examples here. To differentiate this, if I want to differentiate it directly in the form it's in, I'd have to use something called the quotient rule, which I haven't yet mentioned. But I don't need to. In fact, even if I knew that, that would be more work. I would write this, taking advantage of the fact that I can rewrite this as x cubed minus 4x squared all to the power of negative 1. And so that's what the form I want to look at to differentiate. And so if I look at my derivative, my outside function is that I can use the power rule to the power of negative 1. So I have negative 1 x cubed minus 4x squared, that's now to the negative 2, times the derivative of my inside function, which is nice and pleasant, 3x squared minus 8x. Sorry, I went brain dead there for a moment. And now just to make this a bit neater, even though I am done, my numerator, I'm going to write it as -1. I'll just go minus. I'll leave the brackets here. Over x cubed minus 4x squared all squared. All right, let's look at this. I have a quadratic function inside an exponential function. So the outside function is e, so that is exactly the same, multiplied by the derivative of the inside function, which is negative 2x. And that's it, nice and quick. Again, not surprisingly, dealing with functions with a base of e is quite pleasant to differentiate. Although we will later on look at how you can differentiate other bases. All right, the natural logarithm here with a quartic, a fourth degree function inside it. And so to differentiate this, the outside function is the natural logarithm, so it's 1 over the inside function, so 1 over all that, times the derivative of the inside function, which again, is quite pleasant with the power rule. And I might as well clean this up. I get a rational expression. All right, and then I got a cosine function with a cubic function inside it. So differentiate the outside function. Derivative of cosine is minus sine, leaving this as is, and then multiply by the derivative of the inside function. And it helps if I did that right. It's not 3x squared. That's 6x squared. There we go. All right, notice a lot of this is quite quick. And these like this last example, there's no obvious ways to simplify it. Back to the natural logarithm with a sine function inside it. So the derivative of the outside function is 1 over whatever's inside it, sine x in this case, times the derivative of the inside function, which is the cos of x. So I get cos x over sine x, which is the same as something called cotangent, which is not actually something we use in this course. But I'll say that as well. However, cos over sine is just fine. Now I got the other way around. I got the natural logarithm inside sine. So I'm going to put brackets here just to make it extra clear, although they're not really necessary. And so derivative of sine is cosine with ln x left alone, and then the derivative of the inside function is 1 over x. So I'm just going to write this as cosine of the ln of x all over x. Now that brings me to this question, which was actually included in last day's lesson. And so I should get the same answer of what we did last day. Now last day we hadn't learned about the chain rule yet, so we used a logarithm law to rewrite this without that power of 5 there. Well, now that we know the chain rule, we have more options. Not necessarily going to be better, but it should lead to the same answer. So I want to first realize that this 3x minus 4 all to the power of 5, that's the inside function. My outside function is the natural logarithm. And so we differentiate from the outside in. So I have 2 times 1 over 3x minus 4 to the power of 5, multiplied by the derivative of the inside function. And the inside function has actually, you can think of it as a 5th degree polynomial, but there's also a linear function inside that. So there's kind of 3 layers deep here. So I'm now, if I look at what's highlighted in yellow, I'm going to focus on that power of 5. And so use the power rule for that. I have 5 times 3x minus 4 left alone to the power of 4. And now I can differentiate the 3x minus 4. Because essentially, if you look at this, I have a linear function, 3x minus 4, inside a 5th degree polynomial, inside the natural logarithm. And so the derivative of 3x minus 4 is just 3. And so what do I have here? Let's clean this up a little bit. In my numerator, I got 30 times 3x minus 4 to the power of 4 over 3x minus 4 to the power of 5. Well, I got the exact same factor here, 3x minus 4, in the numerator and the denominator. So if I cancel 4 of these out, I cancel all but one of those out. And I get my simplified form of 30 over 3x minus 4. That's it. Well, that's great, and it's done. If you look back in the last lesson at the same question, you will see by using one of the properties of logarithms that when we have this power here, we can write it as a coefficient, you get to the same answer considerably faster. There's always possibilities. There's always multiple possibilities, I should say. But in this case, while the chain rule is great, you probably would have been better off using one of those properties of a logarithm. It's all good. Lastly, I just want to talk about what about the derivative of other exponential functions that aren't a base of e, like any other number? So what if it's a base of b? Well, first, a little property here that we've learned about before. If we look right here, if we take e and raise it to the natural logarithm of something else, these are going to cancel each other out. They're inverses of one another. And so I can see that this is correct. B to the power of x is the same as e to the natural logarithm of b all to the power of x. So I can see these are correct. That said, how is that helpful? Because if I just look at these two, this looks a lot nicer to me than this. Yet, if I look at what I've highlighted in blue, we can take advantage of what we've learned about differentiating with a base of e. So let's differentiate this. So if I want to differentiate b to the power of x, before I differentiate it, let's think of it as e to the natural logarithm of b all to the power of x. But before I differentiate that, let me realize that I have a power raised to another power. So I can rewrite this as e times x to the natural logarithm of b. Sorry. And so now, if I look at this, keep in mind the ln of b is a constant. If the base of this exponential function is 2, if it's 2 to the power of x, then that's the ln of 2, which is some constant. If the base is 3, that's a ln of 3, which is some constant. So the ln of b is a constant value. It's a coefficient of x in a sense. And so I'm going to do one more thing before I differentiate it. I'm going to rewrite this as e to the ln of b times x. Again, the ln of b is a coefficient. And whatever the value of b is, because that's our constant base, I would get a constant value there. So now let's differentiate this. So if I differentiate this now, dy dx. My outside function is e, so it's e to the ln of b unchanged times x times the derivative of the inside function. So this really is a linear function. For example, whatever the ln of b is, again, if b is a 2, if we're looking at 2 to the power of x, then that ln of b is the ln of 2, which is some unpleasant irrational number, but it's a constant number. And so this is a linear function, and that is essentially the ln of b is like the slope of this linear function. And so the derivative of any linear function is just its slope, and so the derivative of what I've highlighted in blue is just the ln of b. And now let's clean this up. If I look right here, I've already mentioned before that cancels out. Sorry, it does, but first I have this little x here. I want to write it instead of as a coefficient, I want to write it as a power. So let me write this as e to the ln of b to the power of x times the ln of b. And now I want to go back to how we started. Again, an exponent, e to the power of the natural logarithm of anything, those cancel out. And so all I have left now is b to the power of x times the ln of b. And that is my derivative. And so in general, if we have a derivative of any exponential function, it's not just a base of e. Well, the derivative of any exponential function is the same thing, right? The derivative of b to the power of x is b to the power of x. But that's not it. It's also times the ln of whatever the base is. So it's still a pretty nice derivative, just not quite as simple as the ln, as a derivative of e. That said, the vast majority of the time, you are expected just to work with a base of e. However, again, it would be recommended that you also remember this. Again, in essence, I mean, this covers everything too. If we have the ln of, I keep saying ln. If we want to differentiate e to the power of x, it's not wrong to say the derivative of e to the power of x is e to the power of x times the ln of e, because the ln of e is just 1. right? This really does kind of cover everything. However, let's erase that and let's stop.